Thanks very much, and thanks to the organisers for having me. I've always heard very good things about the GRDC, well, the WA crop updates, but I've never been to one, so it's good to be here. I guess I'll start by saying that time of sowing is an extremely mature science in Western Australia. There's been a lot of good research done over here over many decades, of which Wal Anderson features prominently in the published papers. But there has been advancements, I suppose, in management in recent times, which I think gives us cause to look at this again. So the research that I'm going to present is largely funded by GRDC through the Early Sowing project across GRDC regions. I'll also talk a bit about some research funded by CSIRO, and I'd like to thank my co-authors from CSIRO and also over here in the West who manage trials and people on the ground, such as Ben Biddulph from DAFWA that make organising trials on the other side of the country a lot easier. So why are we interested in looking at sowing wheat early? Surely this is an old and tired subject, but I think probably many of you that deal with clients and farmers themselves will realise that cropped areas tend to be increasing. And at the same time, whether it's perceived or real, sowing opportunities seem to be decreasing. So it's getting hard to get a cropping program, particularly wheat, in on time. So it's flowering on time. And another sort of reasons that are running in parallel to that is that we can sow early to take advantage of stored soil water from summer fallow rain and long fallow, and we're sort of starting to pay a lot more attention to keeping our summer fallows clean and using that water better. And I guess a slightly frivolous reason is because we can. Now that we've got no-till and can direct drill quickly and easily into very small amounts of moisture or in front of rainfall events, we can establish crops better than we ever had before in hot, dry times. We've also improved our summer fallow management, so often we have stored soil water to help with our establishment, and some insecticides and herbicides and fungicides have become available or cheap, which prevent a lot of the problems that were previous barriers to sowing early. And I guess in the Western Australian context, no-till and dry sowing have been extremely effective in helping farm programs get in on time, but is there something more that we can be doing in order to improve that? So I'll just briefly have a look at what we're trying to achieve when we think about matching a sowing time and a wheat growing time in a given environment. And the thing that's really notable about the Australian environment, as Malcolm says, we grow our crops over the cool season. There's a very big difference throughout the year in terms of how efficiently plant grows. So this is transpiration efficiency for dry matter, for this case it's southern New South Wales, but Western Australia is very similar over the year. And you can see for a C3 plant like wheat, it's transpiring, it's exchanging water for carbon dioxide very efficiently during the winter months, but very inefficiently during the summer months. So the more growth that we can get happening during this period, the more biomass we'll have and the more yield we have. So that's the first thing. The second thing is about getting anthesis in wheat. The time at which anthesis occurs is exceptionally important for yield, is getting that to occur at the optimal time in a given environment. And again, this is very mature science in WA. This figure comes from an ag note from 2005 and really shows what we're trying to achieve in terms of wheat flowering time and trading off, on the one hand, frost particularly, and inadequate growth from too fast development, with water deficit, drought and high temperatures. And we're really trying to get our wheat and as much of our wheat as possible to flower at this optimal time that trades off all those factors. And there's no perfect time to flower in any given environment, so frost and heat usually all happening at the same time, but there is an optimum. And this is a similar way of looking at the same thing coming out of APSIM for a couple of Western Australian environments. This is the relationship between flowering date and yield. And you can see in a central wheat belt environment like Cunderdin, there's this really defined optimum time during the year at which yield is maximised. And that's what we want to try and target as much as possible with our cropping program. So I know there's nothing that winds up Western Australian audiences more than showing eastern states data, but I'm going to tread that line for 4 or 5 slides, so bear with me, guys. But a lot of this research came out of stuff we'd done in the eastern states, so I'll just tell a bit of a story there and we'll lead into the Western Australian stuff. This is the reality that farmers in southeastern New South Wales have been dealing with in terms of trying to get their cropping program in. This is the April-May rainfall anomaly, so the difference from average since the late 1800s up until recently. And you can see that since 1997 there's been a marked decline in the amount of April-May rainfall that we receive. This is Coolamon in the middle of southeastern Australian wheat belt. So Coolamon used to get 80 mils of April-May rainfall, it now averages 40. So that has huge implications for getting wheat established on time, because all our wheat cultivars have been selected and bred to be established in about the first half of May in order to flower on time. So we've got a problem. However, if we look at summer fallow rainfall, so February to March at the same location, that certainly hasn't declined, and if anything, it's increased. So we've got something of an opportunity there to use summer fallow rainfall to establish our crops instead of relying on that April-May rainfall, which has declined. Another way that summer fallow rain and conserving soil water ties in with time of sowing is that if you do have stored soil water present, your optimal time of sowing changes. So this is yield profit output showing the relationship between sowing time and yield in with no plant available water at sowing. You can see the optimums around the middle of May. This is for the Mallee in Victoria. But once you have 50 millimetres available, your optimum shifts back to the 1st of May. But the problem is if you sow the same maturity variety in both of these scenarios, this one's taking on a lot more frost risk. So if you want to take advantage of stored soil water, you need to sow earlier, but you need to do something about the frost risk. So what we looked at initially in the water use efficiency project was using slower maturing cultivars sown early to take advantage of stored soil water. And of course the interaction with the stored soil water was that we can also establish those crops on the stored soil water. So we were interested in comparing sort of different strategies, if you like, to achieve that optimal flowering date. So this is, I guess, most common practice, certainly in Eastern and WA, sowing our mid to fast maturing spring wheats in May. They go through their development stages and hit that optimal date sometime in September. We were interested in seeing whether we could use slow maturing spring wheats, sown much earlier in early to mid-April, or even winter wheats, which you can sow very much earlier because they need to experience a winter before they'll flower, to establish on summer fallow rainfall and still hit that flowering window. So we set up a series of experiments that looked at that, and what we clearly found was that slower maturing cultivars sown early could out-yield faster maturing cultivars sown later by quite a lot, particularly in the presence of stored soil water. So in this table here we have 4 different cultivars of increasing speed of maturity, so Eagle Hawk's very slow maturing, and they've been sown on different dates so that they flower on the same optimal date. And as you can see, these are all elite varieties, so the best in their maturity class out of NVT, and you can see that there's a clear yield advantage to sowing a slow maturing variety early compared to, I guess, what we'd call our main season wheats in May. And that yield advantage comes because the slower maturing cultivar has longer to grow and extracts water to a greater depth. So if we have that stored soil water from long fallow or summer fallow rain, it can use more of it. And you can see that reflected in the water use data. You also have less evaporation because the crop's covering the ground faster and you're covering the soil surface. And transpiration efficiency is higher because more growth is happening during the winter months. When we saw on that graph at the start, transpiration efficiency is very high. So all of that gives you a much higher water use efficiency in these early sown crops. Now the good thing about that is that effect can scale up at a whole farm level. So if you imagine a cropping program where you might have a slow maturing cultivar, in this case such as Bolac, and a mid to fast maturing cultivar such as Gregory, if you look at how they fit into a cropping program, if you've only got Gregory, you can really only start on the sowing on the 5th of May, and you might finish on the 25th of May over a 20-day program, and you end up with an average yield that essentially declines, and it's 4.7 tonnes per hectare. If you can incorporate a slow maturing cultivar which opens up your sowing window into the end of April, start sowing with that and finish with Gregory over the same 20-day period, you increase your average yield to 5.5 tonnes per hectare. So you're picking up yield not only because this slow maturing cultivar sown early yields more, but you're also not getting any of these poor yields at the end of the sowing program. So you have less paddocks going in too late. And in southern New South Wales, that's very readily and rapidly adopted because we've got good adapted cultivars for that part of the world, and people get good on-farm results, such as these farmers at Ardlethan in central New South Wales, who very successfully incorporate a slow maturing cultivar into their program and pick up the benefits of it. Okay, so that's my eastern states indulgence over. I'll move to Western Australia. The problem with Western Australia is it doesn't have that history of breeding slower maturing cultivars. So we don't have the same adapted varieties. All the ones from the eastern states are untested or they're just unavailable. Western Australia has much more Mediterranean rainfall distribution. So southern New South Wales has equiseasonal rainfall, so we get lots of planting opportunities in March and April, whereas that is not the case in Western Australia, most of Western Australia. But we can look at what the value might be using some modelling initially to evaluate what early sowing with a slow maturing cultivar might mean for farm yield. And that's the exercise that we went through initially as part of this project. So what we did is we used APSIM with a frost yield reduction, which has been done in South Australia before, based on these sorts of rules around screen temperature. And we also had a heat yield reduction. Anyone who went to see Paul Telfer's presentation would, I'm sure, have been horrified as to how much yield heat rips off. So we had to take that into account. And we assumed a 20-day wheat program. And we looked at two different strategies. We assumed either current practice, where we had a mid-fast maturing variety only that we sowed, so something like mace, and we'd start sowing in May if there was seedbed moisture, and if that hadn't happened, we'd start dry sowing on the 25th of May in the simulation. And a new strategy, an early sowing strategy, where we had a very slow variety that we could sow early, opportunistically, but then we also had our mid-fast variety that we used in May. So our very slow variety was a winter wheat, and in WA we used mostly a fast maturing winter wheat, which I'll talk about later. And we'd only sow, the sowing window opened on the 1st of April, but we'd only ever plant this variety if we had seedbed moisture. So we weren't dry sowing this cultivar, which is very important. We were only sowing it when it was going to come up. And if we hadn't planted that cultivar in a given year, all of the program went into the mid-fast cultivar. And so the proportion of variety changes from year to year, which most farmers hate the idea of. But anyway, so these are our locations. This sort of gives you some idea of the soil types we used and the capacity in the surface. So in Western Australia, according to our rules, you don't need a very big rain event in order to give you a establishment opportunity, because we're just saying if the top two layers are 50% full, then we'll plant. So even though WA has Mediterranean rainfall because it's got lighter textured soils, that kind of compensates a bit. These are the start of our current practice sowing windows, which you can argue with, but they're what we used. And our slow maturing cultivar was mostly a fast winter wheat. So this is a wheat that has a vernalisation requirement, so it needs to experience a winter, a certain period of cold before it'll go reproductive and start to develop. But once that happens, it goes exceptionally fast. So what that means is that it can maintain a very stable flowering date and flower at the optimum time across a very broad range of sowing dates. Now, the unfortunate thing is that none of those actually exist in released germplasm. But anyway, we'll get to that. So these are the results, and they were reasonably heartening. So this is the average farm yield in each of these environments, assuming current practice. And these are the average yields assuming our early sowing strategy. So if we can have that winter wheat and take opportunities to sow it early, this is the sort of yield that we're going to get, yield increase that we're going to get in this column here. And that's driven by not only the yield advantage of the winter wheat, but also we're getting less late sown paddocks. So we're just taking out those last sown paddocks that get thumped by drought and heat and moving them forward in the program. The other thing you'll note is that there's a yield decline in Mingenew, and that's because in that warm northern and slightly coastal environment, the winter wheats couldn't vernalise that were used in this simulation, so they were flowering too late. So that genotype just isn't appropriate for that environment, and we need to look at slow maturing cultivars that are based on photoperiod. So that's all well and good and encouraging. It was then time to look at experimental data, and there has been work done on this in Western Australia in the past. These are results from Merredin, from Lisa Armstrong, which you can still find on the web. And she compared a lot of different cultivars, but I've just pulled out two from her trials, Osprey and Jans. They're both Eastern States varieties, but I've used them because they're quite highly related through Condor. So you're sort of comparing apples with apples. It would be no good comparing Osprey to, say, Mace or Wild Catcham, because those cultivars are so much better adapted to Western Australia. But what you can see is that in the 3 years of the trial, in the first year there was something of a clear benefit in sowing this winter wheat early compared to our spring wheat in its optimal window later. So that's sort of reflecting the Eastern States trials. In the second year of that trial, there was only a small benefit, and the third year there was a slight yield decrease. So that's the way research sort of works. So the mean increase, or the mean advantage of the slow maturing cultivar sown early was 0.12 of a tonne per hectare. So reasonably modest, but at least there's something there. It's as good as or slightly better than spring wheat sown in May. Mark Seymour at Esperance kindly provided me with this slide. He had a lot of dual purpose experiments which had to be sown early to get the dual purpose benefits. And you could also look at the ungrazed treatments to see what might be happening there. And again, this trial was somewhat heartening, because if you have a look at a winter wheat from the eastern states like Wedgetail, sown early, so the black line there, this black column here, is Wedgetail sown early and ungrazed, sown on the 15th of April, and compare it to, I guess, what you'd call a regional control, which is Mace, sown on the 18th of May. You can see that there's a pretty clear yield advantage there, and there's also the dual purpose possibility in that case. So I guess encouraging results. That brings us to 2014, where the GRDC funded us to do more experiments on this. So we had picked 4 sites across a rainfall gradient in the central and southern wheat belt. We had 3 times of sowing from the middle of April, early to mid-May, and then late May. We sort of tried to make this too early for most WA cultivars. This time of sowing to suit, I guess, your mid-maturing cultivars like Yitpi or Magenta, and this time of sowing to really suit Mace, which was our control. And these were watered up if there was no seedbed moisture. So this year, all the sites had their mid-April sowing watered up. And we included 6 best bet commercial cultivars of varying maturity, and we included 4 near isogenic lines developed by Ben Trevaskis that varied in their maturity genes. So they're a very good tool to use for something like this, because they don't carry any of the genetic baggage that you might have in comparing commercial cultivars. They're largely genetically identical, they just vary for maturity. So these are our commercial cultivars. I won't labour too long on these, they're in the update proceedings. I'd just like you to pay attention to this cultivar here, Whistler, which is that sort of fast maturing winter type that I think should be suited to WA. and most of the time we're comparing it to maize as the local control. These are just an example of the near isogenic lines. As I say, 97% genetically identical. They're in a background that doesn't work very well in Western Australia, but that doesn't matter because they're all penalised equally. And this just shows, these are all different lines from that set that show sort of extreme winter habit over here through to spring habit. These are all being sown at the same time, and you can see the differences in development. So I'll just run through the trial results in the first year. There's only 1 year of results thus far. This is the Doodlakine site as I arrived at sunset and rapidly tried to score by iPhone light. Very dry season at Doodlakine this year, but also low frost. And in those circumstances, the first thing to flower pretty much always wins. So mace sown in the middle of April, even though it was probably flowering in July or early August because there was no frost, yielded quite well. But the thing I want you to pay attention to is Whistler, which would have not have flowered until the middle of September, so took on much less frost risk than planting something like mace that early, but yielded not unreasonably and yielded the same or slightly better than mace sown in its optimal window. This is the Cunderdin field site, which you can see in this photo had a few problems which I think are very important to note in terms of managing early sown crops. It was a wheat on wheat site because we wanted to work with Wanfa at the field day site, but that meant that there was cereal volunteers in our early time of sowing, wheat volunteers, and there was also very high pressure of Rhizoctonia, which affected the winter wheats worse than the other wheats. Magenta and mace just stood up to it a lot better. So at this site, those winter wheats were exceptionally disappointing, and the best yields were achieved by magenta sown early and mace sown later. So I guess you can see the value there already of tag teaming two varieties adapted to Western Australia. This is Wickepin, which is also Ben Bidoff's frost site. And as Ben mentioned, this year there wasn't a heap of frost at this trial site. There was a bit, but not as much damage as we would normally expect, and also a very kind spring. And this site really did reflect what we've seen in eastern states. So Whistler sown on the 16th of April significantly outperformed mace sown on the 20th of May, and they flowered at about the optimal time for that environment, but Whistler was actually flowered a little bit later. So it took on even less frost risk than mace sown on the 20th of May. This is Kojonup, obviously an exceptionally favourable season, but again, another possible downfall of sowing early, particularly with winter wheats. The first time of sowing was overrun by ryegrass and the winter wheats were worse, so I wouldn't put my hand on my heart and say that these were the best that these cultivars could do. And because it was such a kind spring, magenta sown late topped the trial. But yeah, I would point out that even with that winter wheat pressure, there was no significant difference between Whistler sown in the middle of April versus mace sown on the 2nd of June. So yeah, I think I can illustrate that a fast maturing winter wheat like Whistler is able to yield about the same as mace sown in its optimal window on average. Now these are the results from the near isogenic lines averaged across the 4 sites, and I think this is more instructive if anything. The solid black circles, these ones here, are a fast spring wheat. So this essentially represents a genotype that's similar to mace in the way that it develops, and you can see its response to the different times of sowing. This hollow circle here, which start up here and move down here, is the fast winter. So you can see that in the Western Australian environment, the best adapted thing for sowing early is this fast winter genotype. The mid-winter genotype, so this is very similar to the wedgetail and the sorts of things that we generally have in southern New South Wales. It's just too slow in the Western Australian environment, so it flowers too late. And the slow maturing spring wheat, the photoperiod sensitive spring wheat, works pretty well at early times of sowing, but it hasn't got any stability in its flowering date. So once you get to very late times of sowing, it doesn't rush on flower, it just flowers too late and gets damaged by drought and heat. So this fast maturing winter type gives you an exceptionally flexible sowing window and performs very well across a broad early window. Thanks, Peter. So fast maturing winter wheats seem well adapted to the central wheat belt anyway, could have problems in warmer environments. They've got lots of advantages, very stable flowering time, so you can sort of stay away from those flowering frost events, and they also resist stem frost a lot better because they stay vegetative longer. And they're excellent for dual purpose, and Phil Barrett-Leonard's been doing a lot of research on that, and Mark Seymour and DAFRA as well. The bad news, as I say, is that there aren't any in the commercial cultivars for the moment anyway. Whistler, which you saw working very well in these trials, is only AGP in WA. No one's ever bothered to get it quality accredited, so that's its default classification, and good luck finding any seed of it. It was released in 1998, but New South Wales growers, it's still quite widely grown in southern New South Wales because of that extreme valuable winter habit. And I guess some bad news, the only Australian milling quality winter wheat breeding program shut in 2002, and Wedgetail was the last commercial release. Good news is that all of the breeding companies have, I guess, realised the value of winter wheats in our farming systems. They may not be, the big hectares and the main season thing that we're going to use, but they really have a place. And AGT, Advantage, Dow and Longreach have all started selecting for winter lines again, and the first of these are probably 2 to 4 years from release, and I expect that some of them, I've been told that some of them are possibly going to have better adaptation to WA. And I guess just to give an indication of what that might mean in terms of having better adapted germplasm, this is results from a CSIRO trial where we looked at making fast maturing winter wheats by crossing the right spring wheat. So we've got the markers for the vernalisation genes that we need, so we know which cultivars to cross, and we just select the winter progeny, which is what we've done here, and put them straight out into the field as segregating F3 populations, so they haven't been selected for yield. And already, just as unselected populations, they're yielding as well or better than our current crop of ageing winter wheats out of the old DPI New South Wales program. So I think once commercial breeding companies really ramp this up, there's lots of gains to be made. And just to illustrate the robustness of those sorts of wheats in the presence of extreme stem frost, which we had in the eastern states this year, this is one of these fast maturing winter wheats out of a spring wheat cross, standing up very nicely to the horrendous stem frost we had, which, when you sow spring wheats early, just absolutely wipe them out. And even slow maturing spring wheats like Sunvale, just far more exposed to that. So, yeah, it's not something that you can probably take and act on today, but maybe in 5 to 10 years it could be important in terms of productivity gains. And I'll leave it at that.